Professor Antonietti is a professor here at the Department of Mathematics here in Politecnico. She received her PhD in Mathematics and Statistics from the University of Pavia, and she is an internationally recognized expert in the numerical methods for approximation of partial differential equations, and she obtained quite relevant results. Let me just mention the results on numerical methods for on polygonal grids, particularly discontinuous Galerkin, and also numerical methods for the earthquake simulations. For her scientific activity, she also received quite a number of prizes. Let me just recall the recent ECOMAS Jacques-Louis Lyon's Young Investigator Award 2020, and she will fly to Oslo in a couple of days to receive it. And she has been PI of many research grants funded on a competitive basis. And let me just recall the recent PRIN. And but just let me just spend a few more words, because beyond her scientific activity, Paola is also involved in many activity in serving our community at a local level and a national level. Local level, she's member of the board, advising board Polyme 2040 to design the future of Politecnico in the next decades. But she's also member of the National Scientific Habilitation Committee and also of the board of experts of Italian National Agency for the Evaluation of Universities and Research Institutes, VQR. I'm very pleased and to leave the word to Paola. Thanks, Paola.
Thank you, Marco. So thank you, Marco, for this very, very generous introduction. And let me also thank the organizing committee for all their work in making this celebration day possible. So what I would like to discuss today is a recent research line that actually we started less than a year ago on trying to model neurodegenerative diseases. So let me start by thanking the people that have been crazy enough to join for this adventure. So thanks to Alfio, thanks to Luca, and a particular thanks goes to Mattia Corti, a doctoral student that is working with us. And let me also acknowledge Pasquale is over here for putting us in contact with the neurologist of the Neurological Institute, Carlo Besta, that is actually very close to Politecnico di Milano. So the starting point, dementia has occurred in human history a long time before it was the name for the first time. So the first diagnosis of Alzheimer's disease made by Dr. Alzheimer goes back to 1906 when August Dider died. She was a 51 years old woman with 5-year history of progressive cognitive impairment. Alzheimer's disease is one of the possible form of dementia, and is actually responsible of more than % of cases of conglomerated dementia. So since the first diagnosis of 1906, the number of people living with some form of dementia has constantly grown. And in particular, it is expected that by 2050, there will be more than 135 million living with some form of dementia. So these forms of impairment have devastating impact on patients first, their families, and society at large. At the point that the World Health Organization as focused on dementia like a global public health challenge that has to be faced by government as a public and health with high priority. So neurodegenerative diseases refer to a wide range of diseases that feature some common characteristics. They have chronic and progressive development. They have an increased prevalence with age. They are characterized by the destruction of neurons and damage to the network of synaptic connection within the brain. And progressively, they also lead to brain muscle loss. Another common event in progressive dementia is that they are characterized by the accumulation of misfolded proteins and in well-ordered structure that propagates through known paths within the brain. So the fact that accumulation and accumulation of misfolded proteins was known in patient with the conclamated form of dementia. But only 10 years ago, it was recognized that this mechanism of misfolding, aggregation, accumulation, and spreading was the triggering mechanism. And this has been a very important advancement in order to figure out the diagnosis and to try to find some way of treating these pathologies. Despite the fact that there are different kinds of proteins that are at the basis of the triggering of different pathologies, their mechanism, so in the mechanism in which they aggregate and then they spread through the brain, share some similarities. Just to make an example, so for Alzheimer's disease, the most involved protein is so-called the amyloid beta protein. For Parkinson's disease, it is known to be the alpha-synclunin, and for amyotrophic lateral sclerosis, its name is TBDP43. So from the point of view of mathematical models, so what challenges can be realized if one try to tackle such kind of problems? So first of all, there are involved different time scales, and I'll make this point more precise in a second. Secondly, there are many different processes involved, so this is a truly multi-physics problem. There are also the coexistence of many different substances, from the gray matter to the blood to the cerebrospinal fluid. And there are also different dimensional scales in space, from the order of 10 to the minus 9, which is the length scales of the protein scale, up to the whole brain scale, which is of order of centimeters. And finally, there is an intrinsic heterogeneity of the materials. So what are the challenges from the point of view of the modeling and the mathematical analysis and the numerical methods? As I say, the time scales. So while the production of misfolded proteins happens on a daily basis, the process of accumulation, aggregation, and movement happens in many years. At the same time, so from the clinical point of view, these diseases have many overlying symptoms. So it might be very difficult to distinguish among them on the clinical point of view. Then there are what are called by the neurologists the global trends. So misfolded proteins are the triggering event, and of course has to be taken into account. But at the macro scale, our brain put in action some macroscopical compensations. So the two different patients with a similar level of damage might react in a completely different way. And the last one as I said, the insurgence and development of the pathology is highly patient-specific. So they're making a precise prediction on the evolution is really, really difficult at the clinical level. So let's go back. What I'm planning to do now is to discuss slightly more in details each of these 4 pillars. So let's start from the first. So as I said, there are short time scale and long time scale. So what you see in this picture, and I'll try to comment them, is that this is a truly multi-scale problem in time. Because on the graph, what you see on the y-axis is the clinical disease status. So from a normal status to mild clinical impairment up to a conclamated form of dementia. And on the y-axis, you see the state from normal to abnormal. Now, the red line shows the evolution of alpha-beta proteins that are involved, for example, in the progression of Alzheimer's disease. And the green line refers to the evolution of the clinical function. But most important, the yellow line is whenever some sort of damage can be detected from, for example, a structural MRI. So what you can see here is that when you can even detect from images that there's some sort of damage is occurring, the concentration of misfolded proteins is already high. And if you also wait for the clinical function, because of course accessing to this kind of exams is done only based on a clinical suspect, then the situation is even worse. Then, overlying disease, as I said, from the clinical point of view, it's very, very hard to distinguish sharply between different forms of dementia. And this might happen even after many clinical exams. So from this point of view, mathematics, and more specifically physics-based, a combination of physics-based and data-driven models can help somehow, or might help somehow, the clinicians in trying to figure out sharply which kind of dementia is involved. Now, the third pillar, the third challenge is the fact that it's known now that the triggering mechanism take place at the microscopic scale and involves chemical reactions. But macroscopic compensations are equally important in trying to figure out the evolution of the pathology and trying to make possible treatments. But the complexity is very high. So from this point of view, on the one hand, physics-based, possibly enhanced by neural networks can help, but it's not enough. So reduced models that can supplement and that can tame the complexity of the problem could be a viable option. And the last challenge is what I already mentioned. So both the first evolution of the pathologies, as well as the development of this kind of pathologies are highly patient-specific. So in this case, it might be very important to supplement mathematical models with patient-specific data, possibly analyzed in a structured way based on employing artificial network instruments. Then there is the numerical part. So once the challenges from the modeling point of view and from the application point of view has been discussed. Let me just spend a couple of words on what I see are the difficulties from the point of view of numerical analysis. So here, in this context, clinical, patient-specific data are of paramount importance. This means both parameters that somehow fed the model, but also the geometry that can be acquired based on clinical images. And the geometrical complexity is high in this context. There are then, so the need of mathematical models that can tackle both a physiological case and pathological ones. And then to tame the complexity, the dream is to have flexible and efficient numerical solvers that are well suited for high-performance computers environments. So let me just discuss where we started from. So we started from a physiological brain at the macro scale, so the whole organ. And there is a recent, very complete model which has been proposed in this paper, which is of 2020, which models at the same time, based on like a homogenization argument, the pressure, both arterials, capillary, and venous, as well the external fluid pressure, and the tissue displacement. Because when, in the pathological case, which is not the one we are treating right now, after many years of these diseases, the brain literally shrinks. So ill loss is elasticity and gets shrink. So the displacement of the tissue is an important unknown. So if you consider this kind of model at the global scale, you end up with a multiple network poroelasticity system in all the unknowns. Here, with respect to the past, that there is also a second term in the second order derivative in time for the displacement. We discretize this system with discontinuous Galerkin methods, so as to try to mitigate the geometric complexity. And let me just show you the first results. So here on the top, you see for the three pressure fields, venous, capillaries, and arterials. Here is the tissue displacement, and here is the cerebrospinal fluid. Okay, so this is a geometry reconstructed from an healthy patient. Now, what's next? So what I see, as I told in the introduction, this is quite an unconventional talk, so I would like to discuss more what we would like to do than what we have done. So what I see as interesting lines in the field of modeling neurodegenerative diseases. There's the issue of temporal multiscale. So this is the first simulation of the long time scale, so the protein diffusion in the whole organ. This is the simple equation, like an advection diffusion equation, and at the global scale. Then, as I mentioned, for dealing with pathological cases and taking information from physiological ones, reduced order modeling can be a viable option. From the point of view of numerics, there's an issue of whether we can use artificial neural networks not only to learn data that are a very important ingredient in this hybrid physics-based and black box models, but also to make sure that to use artificial neural network-based algorithms to enhance the performance. So to make the algorithms faster. This is an example of an agglomerated grid where agglomeration is fully driven by artificial neural networks to be used in the context of solving at the linear algebra level the system of equation I showed you before, so like in a domain decomposition approach. And then more on the applicative side, there are many things that I think are important. First of all, trying to use machine learning to learn from data, so from patients' data, as well as to try to see whether we can really predict or at least give helpful suggestion to model pathological advancement. And this is, for example, this is a tractography. This is the nerve tracts that can be reconstructed using diffusion MRI. And on top of this, you can solve like a Fischl-Kolmogorov equation, and this would tell you somehow the direction of spreading of this agglomerate of misfolded proteins. And this is the same, more or less the same, the same thing, but I don't know what happens. Here it is. This is how our different regions of brains are connected. This is used to construct somehow the graph of the connections of the different regions of our brain. And with this, I think I can stop here, and thank you for your attention.
So, many thanks, Paola, for this inspiring talk describing the next 20 years of MOX research, at least in 30 or, okay? Are there questions or curiosities or comments? Please.
First of all, thank you for the amazing talk, and also the slides were beautiful. And okay, so very compliments. You've mentioned that when the doctor, when you're able to perform imaging studies, maybe it's too late to detect the, or better, to completely treat the patient well. So my question is very general, and so is when in the clinical pathway of treatments of the patients do you envision to perform numerical modeling?
Thank you for your question. Let me answer in 2 points. So I'll start from what we have been told by the neurologist. So most of the diagnosis process on the patient is not based on clinical exams. So most of the diagnosis is based on cognitive tests. So they have very well structured cognitive tests that are the first stage. And usually people that have some sort of initial beginning of the development of some form of dementia, they start exactly from there. But the process for the diagnosis is very, very long. So on the one hand, one can think of trying to use mathematical models and numerical discretization, and then, numerical discretization and comparison with data from the clinics from the very beginning. Of course, we started from a physiological brain. It's even very much complicated. But the idea is that there is a public database with the images available to everybody, with the images of a very large number of patients, and with their data, of course, not the more, clinical data. But one can think of combining the huge amount of information coming from this database to see whether, if you supplement this plus the physics-based model, you can somehow identify possible path of evolutions that can be used even before the clinical symptoms, because now that the triggering process has been identified, one may think that in 20, 30 years, people at a high risk can be alerted much earlier than when the pathology exhibits the first signs.
So you're talking about prevention?
No, not at the moment. I think that at the moment we are not in the right position with the knowledge that we have right now to talking about prevention, because there are still a lot of mechanisms, this is at least what the physiology told us, that are still to be well understood. But the idea is that first you have to know how to, if you want mathematics to be of any help, you have to know how the physics and how the data can complement in order to be able to make some predictions. Thank you.
Are there other questions or comments, curiosities for Paola?
In the name of the unity of mathematics, can you go back to the equations? I'm sorry to ask for equations.
No problem.
Ok. Ti perdoniamo.
Yeah, that's...
So I wanted to realize what kind of equation.
Yes. This is something like an elastodynamic stuff, okay? Plus you have the coupling here with the four pressure fields, and this is like heat, right? So for any PJ, you have diffusion term, this one, the diffusion term, then the first time derivative, then the coupling here, and here it's a relation between, if one of the pressure increases, of course, you have to take them into account. And this is the model, at least the most recent complete model we found. Usually, the first thing that is done in the literature is to neglect this term. So to work only with some sort of elasticity stuff. Absolutely, absolutely, absolutely. Thanks, Sandro. Thank you.
Thanks. Okay, so we can thank again Professor Antonietti.